Hello and welcome to this next video lesson. It's on the formation of coloured ions. And we have half a dozen learning objectives for this video lesson. The first of which is that we want to know that d electrons move from the ground state to an excited state when light is absorbed. So the light energy promotes electrons from their normal ground state to a higher energy level, which is called an excited state. And that energy difference is given by a formula, which we're going to go over. So that's the first lesson objective. The second one is that each of these transition metal ions has a slightly different energy level between the d orbitals when they're with ligands, and that can be used to identify them by their colour. Thirdly, the colour arises when some of the wavelengths of visible light are absorbed while the remaining wavelengths are transmitted, and that's the same for any colour. And we're going to apply that to the transition metal ions. Fourthly, we want to know that changes in 1. Oxidation state, 2. Coordination number, and 3. Ligand all alter the change in energy, and that's what leads to the change in colour. Right, so all three, 1 or 2 or all three of them, are the reasons why we get a change in the colour. So we also want to know that absorption of visible light is used in spectroscopy. So we'll need to know what spectroscopy is, and we'll have a look also at a simple colorimeter and how that can be used to determine the concentration of the coloured ions in solution. So that's what we're going to do in this video lesson. And why don't we start off with the d electrons. So as you know, the transition metals, when they form ions, they have a few electrons in their 3d orbitals. And all the 3d orbitals, 5 3d orbitals, are all of the same energy level. However, when ligands come along and bond to the transition metal ions, then what happens is some of the 3d orbitals get more energy than some of the other ones, and so you've got like a split energy level. So let's try and draw that pictorially. So what we want is to have our energy level here. So let's just give that a scale. And in a normal transition metal ion, let's draw an ion. So we've got 5 3d orbitals. One, two, three, four, 5. And if we're drawing iron, then we're going to have lost its 4s electrons, and so it's going to have 6 electrons in the d orbitals. Right, so that is an Fe2+ ion on its own without any ligands, but when we get a ligand binding to the Fe2+ ions, as we said, what happens is that these 3d orbitals, the 5 3d orbitals, a couple of them get promoted energy levels. So we can draw those like this. Yeah, so there's our 5 3d orbitals, but 2 of them have a higher energy level than the 3 remaining ones, and so we have to fill in our electrons again like this. So, and then what we can say is that there is now an energy gap between these two of the 3D orbitals and the other three 3D orbitals. So let's call that energy gap. And we'll summarize that by saying it's delta E, energy gap. And so that would be for the Fe2 plus ions. Let's say if it was with a bunch of water ligands. Like that. And it just happens that this energy gap between the 3D orbitals, it just happens that that energy gap is about the same energy as is contained in a photon of visible light. So visible light, lots of different colours making up visible light, each with slightly different energies, but that photon of visible light happens to have about the same energy as this energy gap. So what happens is that if a photon, I'll represent that by a squiggly line, if a photon of light hits this ion, and let's say it hits one of these electrons in the 3D orbital there, then it's going to give that energy, the photon's energy is given to the electron, and so the electron is promoted from the lower 3D orbital to an upper 3D orbital like that. So you can see that the light that is shone onto the solution of transition metal ions is not the same as the light that comes out of the solution of transition metal ions, because some of the light has actually been absorbed by the ions in order to promote that electron from one 3D orbital to the slightly higher energy 3D orbital. And so it's that difference in light that exits the solution compared to the light that entered the solution that gives it its colour. We're going to go into that in a little bit more detail on a later slide. But for now, what you need to learn is that it's the ligands change the energy levels of the orbitals, and the energy gap that results is about the same as the energy of a photon of visible light. So when the photon hits one of those electrons, it can promote it up and therefore absorb that visible light photon. And the energy of this photon, let's just give it an E here. So the energy, or you could say the change in energy between the d orbitals, can be worked out from the following equation. Delta E equals hv, where h is Planck's constant, and v is the frequency of the light absorbed. And that would need to be in hertz. And Planck's constant, as it happens, is 6.63 times 10 to the minus 34 joule seconds. And we can also express this in a slightly different way, because V can be related to the wavelength via the speed of light. So you can also say that delta E is hc over lambda, where c is the speed of light and lambda is the wavelength of that light absorbed. And wavelength is measured in meters, and the speed of light is about 3 times 10 to the 8 meters per second. And this energy gap here, this energy gap, it depends upon 4 things. One is the actual metal ion itself. In this case we had an iron. It depends on the oxidation number of that ion. In this case we were dealing with a 2+ ion. It also depends upon what ligand is involved. Right, in this case we were dealing with water, and it depends also on the coordination number. Which in this case was 6. So those 4 things determine the energy gap, and in turn the energy gap, and therefore the frequency of light that's absorbed, determining the colour, they identify the metal ions. So we can use the energy gap and the resultant colour of the solution to identify metal ions. So let's just dwell on how these metal aqua ions are so colourful. Here we have a blue sample. It's actually a cobalt iron solution where the ligand is a chloride. And let's assume that we've got some white light. So we're going to approximate white light with some red. Some red light is incoming. We've got some yellow incoming. And let's say we've got some purple light incoming as well. So that's white light, and that comes through. And what happens is that the red light goes all the way through, and the purple light goes all the way through, like that. But the yellow light gets absorbed by the 3D orbitals. All right, so let's just remind ourselves what's going on. We've got a couple of promoted 3D orbitals, and we've got 3 3D orbitals that are at a lower energy level, and this is our energy gap that corresponds to the energy that is the same as the yellow light. So this yellow light has shone onto one of these electrons and promoted it to a higher energy level, and has therefore been absorbed. So the yellow light has been absorbed and stays there, and so it doesn't come through the solution. Okay, so when the light comes out through the solution, the resultant light, right, has no yellow element to it, so it's no longer white, and it actually appears blue. So let's switch to blue, and so this looks like a blue colour, and that's what makes it blue. That it's lost some of its yellow light, and so the white light minus the yellow light looks blue. That's why it's blue, and the yellow has been absorbed by the electrons that have been promoted to the excited 3D energy levels. So just returning to the learning objectives for a bit, let's just check what we've done already. I think we've seen that the d electrons move from the ground state to an excited state when they're given some energy to do so, and that energy comes from visible light, and that energy difference is given by delta E equals hV, and because V equals c over lambda, delta E equals hc over lambda. So that's the first lesson objective we've done, and we've stated that these transition metal ions can be identified by their colour, because that energy difference is slightly different from situation to situation. So we've done that, and we've also done the fact that colour arises when some of the wavelengths of visible light, in our example, remember that yellow was absorbed, while the remaining wavelengths are transmitted through, and that's how the colour changes, and that's why we see the solutions as coloured. So we've done those three lesson objectives now. Give them a little tick each, and so what we can now go on to is to look at the list of 3 or 4 things that determine the difference in energy level between those 3D orbitals, and that is the oxidation state of the metal ion. We looked at ion 2+, so it's a 2+ oxidation state. Also a coordination number. For example, we had 6 water ligands attached to our metal ion, so the coordination number affects that energy gap. And also which ligand it is. For example, we had water, it could have been chloride, and that ligand will also affect the energy gap, and therefore the colour. So that's what we're going to deal with in a little bit more detail now, and we've still, after that, got to do a bit on spectroscopy. So just quickly on colour before we get onto oxidation states and coordination numbers and ligands. I just want to make sure you understand where the colour comes from here with a transition metal ion. So what I've got here is a picture of the electromagnetic spectrum, and sort of just left of centre is the tiny bit of the spectrum that is visible light, and that's highlighted. And then you see all the colours in visible light going from indigo at the high energy side down to red on the lower energy side. So as we've mentioned, when an electron gets promoted to a slightly different energy level of 3D orbital, so let's draw our 3D orbitals like this. They should all be about the same size as boxes, but let's draw here a larger energy gap. Right, so this is supposed to be a larger energy gap between the 3D orbitals. And I've drawn that here because that's going to correspond to a higher energy level of visible light that's absorbed. Whereas on the lower energy level of the visible spectrum, what you're going to get is you're going to get a slightly smaller energy gap between the 3D orbitals. So these are the 3D orbitals again, and you can see we've got a energy gap that's smaller. In this case, and so a lower energy photon, i.e. a red photon, is going to be able to promote an electron from one of these orbitals to one of these orbitals, and so it's a red photon that's going to be absorbed in this case, whereas in the first case it would be probably a blue photon that would be absorbed to make the promotion from this orbital to this orbital. Okay, so that's not going to be examined. I just wanted to help you fully understand how the transition metal ions have their colour. Okay, so this is the bit about identifying transition metal ions that you could be examined on, and let's just repeat that it's the colour of the transition metal ion complex that identifies it. And where does the colour come from? Well, the colour comes from the energy gap, as we've been through. That's the energy gap between the 3D orbitals. And what affects the energy gap? Well, three factors affect the energy gap, and so the colour is specific to not only a transition metal ion, but the transition metal ion when it's determined by individual factors. So let's go through that now. First of all, let's draw out our 3D orbitals with our energy gap. Okay, so this is our energy gap between our 3D orbitals that we're talking about, and what we want to discuss is these three factors that affect the size of this energy gap and hence the colour. Okay, so factor number one is changes in oxidation state. Alright, so that if the oxidation state of the complex changes, then the colour will change, right? Because the energy gap has changed. Okay, let's give you an example. If you've got an iron aqua complex, such as this one, with a 2+ charge, then that's going to be a pale green colour. So let's try and highlight this in pale green. Whoops, let's maybe just circle it in green. Then that would be green. Okay, now going back to black, let's then state that if you then had a similar complex, still an iron aqua complex with the same number of ligands and the same ligand, but it was a 3+ charge, then that would then be yellow. Okay, so let's just try and highlight that in yellow. So that one's yellow because it's 3+, and the first iron aqua complex 2+ was pale green coloured. And so that is oxidation state. The second factor that affects the size of this energy gap and hence the colour is the coordination number. So the coordination number, you remember, is the number of ligands that are hanging off the metal ion. And let's, in a similar way, go through an example. So if we then have a look at a copper aqua complex, so copper aqua complex where there are 6 ligands, and that has a 2+ charge, then that's actually a blue colour. So let's draw a blue box around that one. However, if the coordination number of this copper complex, or a copper complex, was changed to 4, so there would be, in this case, 4 chloride ligands. It happens to have a change in a charge of 2- ions. Then the coordination number is 4, and the colour of this complex is yellow. And the third factor that changes the size of this energy gap is the actual ligand. the actual ligand changes, can change the colour. So another example, let's have a look at a cobalt complex this time. So when cobalt is complexed with water in a cobalt aqua complex, 6 of those ligands, happens to have a 2+ charge. That's actually a pink colour, and I don't really have a very good pink on my spectrum here. Let me use this to represent pink. But when we change to a cobalt ammonia complex, also with 6 ammonia molecules in the complex, also with a 2+ charge, then that would be a straw coloured complex, and I don't have straw either, so I'm going to try that in yellow as well. So you can see that unfortunately it's not quite as easy as saying, for example, that iron complexes are yellow, because you can see here there's 3 sort of versions of yellow, all with different metal ions in the complexes. So unfortunately what we have to do is we have to remember the whole combinations of oxidation states, coordination numbers and ligands for each of the common metal ions. And in your exam you may well have to identify a complex from its colour, so there's a bit of memory work to do there. Okay, so let's just check off our 4th learning objective. We've seen how changes in oxidation state, coordination number and ligand alter the energy gap, and how that leads to a change in colour. So the last thing that remains to be done is to have a look at spectroscopy. So what do we use spectroscopy for? Well, it is used to determine the concentration of a solution, and it does that by measuring the amount of light that is absorbed. And a typical setup would look like this, where on the left you have a light source, and that shines white light to a filter, and the filter just lets through light of a certain wavelength, and that is the appropriate wavelength for the sample. That is the wavelength of light that is absorbed when the electrons are promoted from one 3D orbital to another 3D orbital. So you shine that light of a particular wavelength through the sample, and let's say that we have lots of photons coming in here. They're all of the same wavelength, so I've drawn them all in blue. But on the way out, you get fewer because some of them have been absorbed by the sample. And the colorimeter just measures the intensity of the light coming through. So intensity of the light that has come through the sample. So obviously a more concentrated solution of the sample will absorb more light. More concentrated solution absorbs more light. And this is what a colorimeter might actually look like. This is a real colorimeter, and you can see the student is putting a sample into the colorimeter so that you can measure the light being shone through it. But we're not quite there yet. What we need to do is use a calibration graph first to get our actual answer. And so you'd start off with 2 samples. Let's say you've got a sample of known concentration. All right, and another sample that you're interested in of unknown concentration. There's supposed to be a bunch of question marks there. And what you do is you put your first sample through the spectrometer, and you would measure the relative absorbance. So let's take one sample, all right, and you'd measure the relative absorbance of that. But what you would do is you would need to take several samples to get sketch a graph of, and you would dilute each one. So you would start off with the concentrated sample, then you dilute it, and then you dilute it some more. And you'd send each of the samples through the spectrometer and plot a point for each one. So you'd get some sort of plot like this on the y-axis. We would plot our relative absorbance. And we plot that against the concentration. And this is our known concentration. And we dilute it by known amounts. So we've got at least 3. Let's say we had 4 points. So when we put our most concentrated solution through our spectrometer, let's say our relative absorbance was, well, let's say it's 0.4. Okay, so we're going to put a point here, and then we took our second sample, so we've diluted that a little bit, and our relative absorbance might have been 0.3 for that one. And then our third sample might have been 0.2, and so we plot that like that, and 0.1. So we get some sort of plot, and then we draw a line of best fit through that. And that's what we've done with our known concentrated sample. Now we come to our sample of unknown concentration. And that's the concentration we want. And we put that through our spectroscopy machine. And let's say we find that its relative absorbance was 0.25. So then we take that point, 0.25, and work its concentration out. From the calibration graph. And that would give us the concentration of our unknown sample. Like that. And the last thing you need to know about spectroscopy is just the reason why we might use spectroscopy to find the concentration of a sample. So let's just write that in the corner here. Why spectroscopy? Why is this a good method to work out the concentration of a solution? Well, 3 main reasons. It's easy and quick. Second reason is that you can measure low concentrations and still get quality readings. And the third reason main reason is that it doesn't interfere with the reaction. We're not actually doing any chemical reactions here. That's good. And they'd be the three main reasons why spectroscopy is used to work out the concentration of a solution. So that's it for this video lesson. I hope that's been clear enough. Let's just go through our learning objectives, make sure we've covered them all off. Do we know that d electrons move from the ground state to an excited state when light is absorbed? Yes, we do. And do we know that we can work out the energy gap from that equation involving Planck's constant and the wavelength, frequency and speed of light? Yes, we do. At least we did it. And do we know that transition metal ions can be identified by their colour? Certainly we do. And that colour arises when some of the wavelengths of visible light are absorbed when the electrons are promoted from one 3D orbital to a excited 3D orbital. And the rest of the wavelengths are transmitted through. So we know that, and we did that. We also know that change in colour results from altered energy gaps, and the energy gap is altered by three factors, one of which is the oxidation state of the complex, another which is the coordination number, the number of ligands attached to the metal ion, and the third one is the actual ligand that is involved. So those three factors change the energy gap between the 3D orbitals and hence change the colour, and that's what's used to identify the metal ions. And then the last two learning objectives were on spectroscopy. And we found simply that visible light being absorbed is what spectroscopy is, and we went through a simple method using a colorimeter to determine the concentration of a coloured ion solution involving a calibration graph. So yes, I think we've done all those. Hopefully they've been clear. If not, watch the video again and then ask me any remaining questions. Thank you.